Hello everyone, and welcome back to Plane Time. We are broadcasting live and in the clear today from our studio in Orlando, Florida. And we had a very interesting interview earlier today with Mr. Ben Templeton, a young pilot from South Carolina who flew all around the United States in a J3 Cub in a 35-day ordeal, 107 stops, and just a wonderful experience for him. And it was great to hear Ben's story and to learn more about him and his exciting trip, as well as his potentially great future. So it was wonderful to have him. But you know, while he was en route on his trip, he had to depend on good weather for flying. And that's the case with all of us as pilots. We need to have a good understanding of weather and its possible impact on our day's flight. This is probably one of the subjects that pilots are maybe the least familiar about. They know about their airplane, the aerodynamics, the operating characteristics of the airplane, how it stalls and the like, but the impact of weather on our flying is not as well understood by pilots as it probably should be. Today, we're going to try and fix that, or at least in part. Our guest today is Dr. George Bartuska from the Lakeland, Florida area, and Dr. Bartuska has a doctorate, and his studies have been in meteorology. He's not a stranger to Plane Time. He's actually been here before in January of this year and in May of this year, and he's back with us again. And today, Dr. Bartuska and I are sitting in the midst of what looks like a science experiment in a laboratory. Dr. Bartuska has brought with him many of his props that is going to help him explain new information to us and bring us up to speed on this wonderful atmosphere that surrounds us here on planet Earth. And we'll learn a lot more about the phenomenon and the science of weather. Dr. Bartuska, thank you for joining us today. It's good to have you back again. Thank you very much. Thank you, Ron.
What we want to do today, in January, we had started with an introduction to meteorology, and in particular, the meteorology that experienced in Florida. In June, we did a quick review of hurricane weather or tropical cyclone weather. What we're going to do today is a continuation of what we started in January, but today's title is Atmospheric Stability Part 1, because there's no way I can get through all of atmospheric stability in 30 minutes. We're going to do Part 1 today, and then Part 2 probably in December. What I want to start out with, if you can go to my screen, what I want to start out with today is where we're going to end up in December. Once you've gotten your standard weather briefing for flying, there's all kinds of information available from the National Weather Service, this being one. And where is, oops, sorry. Here we go. So this is the risk. This is today's data. This is the risk. There's not much severe weather out there, but let's say you were going to be flying in the area of Georgia or Alabama, and you wanted to know more about that weather. It turns out that we can go up to forecast models and bring down, if I can get that to stay, observed sounding records. We take radio zone soundings every day, twice a day, and I'll go into that in a minute, and I'm going to try my best to pull one up for Atlanta. So the question is, this is a skew-Teague diagram, and the question is, what does this really mean? Well, that's where we're going to end up in December. We're going to introduce all the theory behind it today. Today I'm not going to talk about environmental lapse rates or dry adiabatic lapse rates. We're going to do all that in December. Today we want to do the background. Now I'm going to switch to my PowerPoint. There we go. So, Introduction to Atmospheric Stability Part 1. It's not changing. There we go. Now, first thing we want to start out with is understand something. People who fly powered aircraft, people who fly gliders, and people who fly hot air balloons all need licenses through the FAA. And as a result of the lower right-hand corner, which is the new world, so to speak, in the last 20, 30 years of people who've been trying to understand what causes tornadoes out in the Midwest. This is a university team with a rolling Doppler radar, but you've all heard of storm chasers. That whole world has actually contributed to meteorology by simplifying a lot of things so that people that aren't trained meteorologists can understand them. Well, I'm going to real quickly go through the presentation I made in January. We started out with why are there thunderstorms every afternoon in the state of Florida? I actually introduced atmospheric stability with this picture that I'm going to come back to later in the talk. This is on the beach at South Daytona Beach. And we talked about what generates a sea breeze and how Florida is unique to anywhere else in the world that I know of, where we have a Gulf water on one side and we have the Atlantic Ocean on the other side, and we generate a dual sea breeze that causes this rolling in of air over the center of the state of Florida. And if there was no other weather systems happening at the time, we would basically have thunderstorms right down the middle of Florida every afternoon in the summer during the rainy system. But we do have other weather systems, air masses, upper airflow and stuff. So we could have a situation where the weather forms over Florida and then moves west, or then moves east and then moves west. And all kinds of things can happen. And then I pointed out after World War II, here in Florida and in Ohio, the National Weather, well, it's called the United States Weather Bureau then, and the Navy and the Army Air Corps, which became the Air Force, did a program to try and understand thunderstorms after we lost a lot of pilots to thunderstorms during World War II. This project was called the Thunderstorm Project, and there's a marker you can read about it. They basically took 5 of these aircraft, P-61s, and they flew them in thunderstorms at 5,000, 5, 10, 15, 20, and 25,000 feet, which must have been the ceiling at that time for supercharged radial engines. And they took enough information that is where we have this information of the stages of the thunderstorm that's reproduced in every textbook on meteorology. And by the way, we never want to fly into a thunderstorm on purpose, but in this case, we did it because we needed to somehow figure out what was on the inside of it. And here's the type of thing that's in every textbook about the cumulus stage, the mature stage, and the dissipating stage. Now, this is the introduction to what we're going to start talking about today. This is known as a skew-T diagram. I'll talk much more about it next time, and we'll talk about environmental lapse rates, dry adiabatic lapse rates, and wet adiabatic lapse rates. And if you're not an engineer like I originally was, that probably is freaking you out, but don't worry, we're going to simplify it. Now, we have surface observations that we see on a surface map, but we also need to know about what's happening above us. And to do that, we use weather balloons or radiosones. And the basics, the weather balloons measure the temperature, the humidity, and the barometric pressure up to 100,000 feet typically. And we launch them every day at 11 and 2300. It says here it takes about 45 minutes to an hour for the balloon to go up. Originally we used all helium, now we're using a lot more hydrogen because of the shortage and cost of helium. And there are about 1,000 stations worldwide that we can get this data from. But all this started with getting data from flying aircraft and putting recording instruments on the struts of the aircraft. And that was back in the 1920s and 1930s. But it became obvious after a while that the radiosone was the way to go, and starting in 1929, we started to launch balloons routinely. And like I said, now we launch them twice a day at all these locations. Here's the typical radiosone that's in use today with the antenna, a high-tech pressure sensor, a GPS transceiver. This is the temperature sensor, and this is the humidity sensor. This is the type of radiosone that was in use till about the 1980s, after World War II up to then. And this is one that was used in the 1990s. And I happen to have one of those here with me. It's very light. This one doesn't have a battery in it. The black area, flat black area, is in there to keep out external radiation. The humidity sensor, the humidity sensor is on the inside right there. And it doesn't have a battery in it right now. That would go there. These are expendable. When they've come down, there'll be a message on the package telling you the people where to send it back, but they only get about 20% of them back because they're either thrown away or people keep them for souvenirs. Also, in the previous ones, before they had electronic pressure measurement, they actually had the equivalent of a barometer or altimeter inside to get the pressure, but the newer ones don't have a big unit like that in it. Okay, back to the PowerPoint.
George, if I can
Yeah.
break in just a moment. So it's interesting you should mention the radio sounds, and that brings back a memory to me. One of my grandsons, when he was as little as 5 years old, indicated an interest in weather, and he was fascinated by thunderstorms, and we lived in North Texas, which was in the middle of Tornado Alley and the like. So my wife and I took him to the National Weather Service office there in Fort Worth, Texas, and he got to watch a radio sound being launched, and he was just absolutely thrilled. Today, that young man is a weather service officer for the United States Air Force, and he's stationed at Vandenberg Air Force Base, and I'm
Very cool.
incredibly proud of him.
Good. Me too. That's great. That's great. And I've had the opportunity with National Weather Service training to launch 2 balloons, officially with weather, and I launched one with a NASA program and another one at a school in town here. There's a big thing now to put a GoPro camera on a home-built spacecraft, we call it, and it'll go up to about 100,000 feet. And we were lucky, we did this about 3 years ago. The thing you're worried about is where is it going to come down? Is it going to come down in a tree? Is it going to come down in a lake? We were lucky it came down in Winter Haven right across the street from a cement plant in a tree that was only about 10 feet tall. So that, we were lucky.
You were able to retrieve it.
That's it. Okay, now back to the PowerPoint, please. Now, keep in mind, we launch these balloons every day at midnight, Greenwich Mean Time, Zulu time, UTC time, and 12 o'clock noon. So 12 o'clock midnight, 12 o'clock noon, which transverses to Eastern Standard Time, 8 a.m., 8 p.m., regardless of the weather. And I want to make sure that I mention there are other sources of upper air information. Radar wind profiler that is basically a radar antenna sitting on the ground that shoots radar energy, electromagnetic energy straight up. There's other ones that use both radar and acoustics to do the same thing. And then we have ACARS, a system that automatically takes certain amounts of data that's available to us from the airlines that are flying all over the world. And if you watch the news much, you know about 3 months ago there was an article in some of the magazines where the National Weather Service and the World Meteorological Organization mentioned that we weren't getting a lot of data because a lot of airliners weren't flying. We were missing a lot of data. And remember, we only have a few weather stations over the ocean. The Earth is covered about 70% by ocean water, where there isn't a lot of data coming from. So any other source we can, like aircraft, is good. And then, of course, we have satellite data, satellites that can get us some of this data. Now, we're kind of jumping ahead. Let's back up for a minute. What about clouds? What in the heck keeps them up there? And these massive thunderstorms that obviously have a lot of water in them, and a hurricane, which technically is a tropical cyclone that could have millions of pounds of water in it. What keeps it up there? Well, it must have something to do with density and buoyancy, and that's what we want to talk about next. Hot air, as most pilots know, hot air balloons rise because we put hot air in them that's less dense than the surrounding air, and all pilots in their training have to learn the characteristics of less dense air. Now, I'm going to ask your forgiveness for this slide because it violates the basics of PowerPoint presentation of only having 6 bullets with 6 words per bullet. But this is one of the most important things I'm going to talk about today because it not only applies to pilots, it applies to meteorology. Notice what it says. Dry air is 78% nitrogen, 21% oxygen. If you went into a group of people anywhere who aren't pilots and you asked them the question, what do you think is more dense, moist air or dry air? Well, most of those people would raise their hand and say moist air because it's full of water. But it's just the opposite. And why is that true? Well, as we said, the air of the Earth is made up of 78% nitrogen and 21% oxygen. Nitrogen and oxygen are both diatomic atoms that become molecules. They only occur as twins together. And nitrogen has an atomic mass of 14. That means as the pair, its weight is 28. And oxygen has an atomic mass of 16, and they only appear as pairs, so they're 32. So you combine the oxygen and the nitrogen that's out there, you get a basic weight of 60 atomic mass units. Well, water vapor, H2O, you have 16 atomic mass units for the oxygen and 1 each for the hydrogen, so it's only a total of 18. Well, if you have a lot of water vapor in the air, it's going to displace the nitrogen and the oxygen, and the atomic mass of that property is only going to be 18 versus 60. So the result is, and I hope that helped explain that to you, the result is that the atmosphere that has a lot of water vapor in it is much less dense than dry air. And so what does that mean? We always teach in flight training, that makes the wing less efficient to generate lift. It makes a gas turbine less efficient to generate thrust. It makes the propeller less efficient to generate thrust. And it makes a reciprocating engine less efficient to generate power. So, and all this is going to transfer right into weather. Now, temperature. We all take this word for granted, temperature. Okay, it's 60 degrees out, say Fahrenheit. But what does that really mean? And when we look at a thermometer, and we take for granted, we don't tend to ask the question, what makes that go up when it gets hot? Or what makes it go down when it goes down? Most people will guess that it's the pressure or something, but it turns out it has nothing to do with that. It has to do with the fact that temperature is a measurement of kinetic energy. It means that the molecules are vibrating. It means the molecules are vibrating. I have here a tuning fork, and I'm just going to hold it up to the mic a little bit. So when you think of temperature, you need to think of vibration. And when things vibrate, they get bigger, they expand. When they're not vibrating as much, they get smaller, they shrink. If we think about bridges, so if there's a steel bridge and it's 20 degrees below zero out, all the steel work of that bridge is shrinking. If it's in the middle of the summer and the sun's beating down on it and the atmosphere temperature is 95, the temperature of the bridge itself might be 150 degrees, and it's stretching. So as a result, we have expansion joints in bridges, and it's also a factor with aircraft. You may not have thought about it, but take a Navy F-18 taking off from somewhere in Florida, where once again the atmospheric temperature is 95 degrees, the aircraft might be 150 degrees, and he or she takes off and climbs up to 30,000 feet. All of a sudden the temperature is 60 degrees below zero. Well, that plane is made up of aluminum, magnesium, composites, stainless steel, and all those properties expand and shrink at a different coefficient. And so the designer of the airplane's got to keep that into account. Okay, so that's temperature. Let's go back to the PowerPoint, please. And we see here thermal energy. It's the total energy potential and kinetic of all the particles of an object. So if it's really hot, the atoms are moving around, and if you add moisture to it, now it's not only less dense, the atoms and molecules are farther apart, that makes it even less dense. Now the next thing we think, we don't talk much about evaporation, but evaporation is really important for two reasons. One, it's the way all the water vapor gets into the atmosphere, and two, it's what makes the most important instrument we have for these subjects, which is a sling psychrometer, work. And before I talk about the psychrometer, Ron and I are going to do a little experiment that we need that right now, that I encourage you all to do at home when you have a chance, if you can come back to me for a minute. You can take a cotton ball or a piece of gauze and just get it a little bit wet and rub it on your forehead or rub it on your arms. And what do you notice, Ron?
Well, it feels cooler where I just rubbed it.
In fact, exactly, it feels cooler because evaporation takes energy. We call it the vaporization coefficient. And our bodies are giving up some of that 98.6 to convert that water from a liquid to a gas. Okay, I'll come back to that in a minute. So that's evaporation. So if evaporation is a cooling process, could I have my slides again, please? I have a picture here of people at the pool. This happened to be the pool here in Lakeland. All of you at home have at some time either just got out of the pool or got out of the lake or got out of the ocean and noticed that you're cold. Even if the water's warm, right now the water in Florida in the Gulf is at least 80 degrees this time of the year, Fahrenheit, and can be around 80 on the Atlantic, and yet you get out of the pool and you're freezing because your 98.6 is converting that water that's on you to gas. Well, it turns out condensation is just the opposite. In the case of condensation, and we have a glass of water here with us. There's a little bit of ice on it, a little bit of water on the outside of it. But when condensation takes place, it's cooling the air below down to the dew point. The dew point is the temperature at which the water vapor starts to come out of the atmosphere. And if we were not in an air-conditioned studio, you'd see a lot more water on the outside of my cup. And in my slide, we see some there. And it says it's a temperature at which water vapor changes from a gas to a liquid. And I'm going to move this down for a minute now, and I'm going to show you how we measure that. And this is why evaporation and condensation are so important. If you can get the camera on there. This is a sling psychrometer. These come in about 5 different shapes and sizes. They cost about $100 a piece. Notice there's 2 thermometers. One has a wick on the thermometer. That's called the wet bulb. And there's a reservoir of water underneath here. And the other thermometer has nothing on it. That's the dry bulb. And what we do with this is we sling it. We whip it around like this. And the main thing when you're using a psychrometer is you don't want to do it in the sun because we don't want to measure the temperature of the solar radiation coming from the sun. And we will stop and not putting our hands near the bulbs of the thermometer, we will read them. And then in the old days, we would go in the book and look in the table. Today, you can take your cell phone and bring up a calculator and get the relative humidity and the dew point.
And so, George, what you've measured there is something we call a wet bulb and a dry bulb temperature. Is that correct?
Yes.
So you're measuring both with one instrument, the sling psychrometer.
Right. And it's based on the ability of the water to evaporate off that wick. Now, if the relative humidity is 100%, there won't be any evaporation. You can't have evaporation, so both thermometers will be measuring the same temperature. Okay? And we're going to be.
And so, as pilots, as we're getting weather brief, and one of the things that we listen for, and our antenna goes up, is when the temperature and the dew point are within 3 degrees of each other. That would give us an idea of relative humidity on the rise. If the temp and dew point get real close, we're in a high relative humidity, which has various connotations to pilots, oftentimes restrictions to visibility.
Exactly. The number that's in most of the books is a 5-degree spread, and in my first talk, I talked about, to relate it to the public, I talked about fog. If the temperature and dew point are within 5 degrees, there's a good chance you could have fog on the ground, or you could be having some kind of precipitation. But absolutely, we follow that. Okay, now we've done evaporation, condensation. Back to the slides, please. Now I'm going to talk about this scene again. This is South Daytona, but it could be anywhere. We're going to pretend that this is our car right here, and we get out of the car, we lock the car, and we go swimming, and we're out there swimming for about an hour. And in the meantime, the car is a greenhouse. The sun is heating up the inside of the car, and the car maybe gets to about 150, 180 degrees. We come back out of the beach and open the car door. 5 minutes, okay. Open the car door, and a bubble of air comes out. We're going to talk next time about that bubble of air, because that bubble of air is a partial in meteorology, and I'm going to go into that next time. And this is the diagram that we're shooting for. Oops. Just a minute here. I want to back up. Okay. 5 minutes. As I said, I open that car door and the bubble of air comes out. Well, that bubble of air is dry. There's no water inside that car, and that bubble of air is just like a hot air balloon is going to start to rise, and it's going to go up, and it's going to go up to maybe around 5,000 feet. We'll just hypothetically pick a number out of the air, and at 5,000 feet, it will have expanded and cooled to around the same temperature as the surrounding air, and it will have stopped. That's it, nothing else. And eventually it might start sinking down again. But now let's change the story. Now we came back to the car, we dried off with the towels are all soaking wet. We throw the towels back in the car, and we see there's a hot dog truck down the beach. We lock up the car again, we go down the beach, and we're down there and we run into some friends, and we're now down there for an hour or an hour and a half. In the meantime, those wet towels have been inside the car cooking with the heat and all evaporating the water off the towels, making that air fully saturated, making the humidity 100%. Now when we come back to the car and open the door, we get a partial or bubble of air that comes out again, and it's going to rise again just like it did before, only not quite as quick. But here's the interesting thing that's going to happen. It's going to go up again a little slower, and it's going to expand, and this time, we'll just pick a number out of the air, around 5,000 feet, it's going to have cooled to the temperature of the dew point. And now that's at the lifted condensation level, which is shown in this drawing, the LCL. It's now ready to start doing two things. When the condensation takes place, remember the heat is given off. Now it's getting warmer. Depending on the environmental conditions, if it can start to rise, now it's going to be what we call the level of free condensation, or free condensation level, where on its own it's going to start going up, and it can get going 60 to 100 miles an hour. And this is the source of updrafts. This is the source of thermals for glider pilots. It's the source of updrafts for thunderstorms that can lead to tornadoes, and the source of updrafts for hurricanes. So the bottom line is that water is the dynamite of weather. If we don't have water in the atmosphere, there isn't going to be any severe weather. Okay? And so, it will continue to go up. Just a minute here. Now this is a graphical version of what I just went over. Here is LCL is the lifted condensation level. That's about 5,000 feet in our example. The level of free convection is where it has now started to condense enough and warm up enough that it's hotter, becoming a hot air balloon, and it will rise until it gets to a point where it finally has given off all its heat and it's equalized to the level of surrounding air. This area that's in green is we call CAPE, the convective available potential energy, and those are the kind of things that I'm going to talk about next time. So next time we're going to talk about environmental lapse rate, dry adiabatic lapse rate, wet adiabatic lapse rate, and that's the end of part one. I think that's everything I wanted to talk about, Ron.
Wow. Well, George, this has been great. Dr. Bartuska, your knowledge and your skill, of course, is widely known. Educated first at Purdue for undergraduate and then at Orlando University. You spent some time dedicating your services to the United States Navy. Thank you for your work there with the Navy and your defense of our country. It's great. And you've been a long-time enthusiastic supporter of the Florida Aviation Network, now giving us some much-needed training in atmospherics and weather phenomenon that we can all take to heart as pilots and learn from. So the dynamite of the atmosphere.
The dynamite of the atmosphere is water.
I see.
And I wanted to leave...
You don't have to mix it with vodka or anything like that. Is that correct? I mean, I've been doing this wrong all the time, I
That's
guess.
right. And I did want to leave, if you want to get ready for the next lecture, these are the two books to start referring. The FAA's latest edition of Aviation Weather, that has 2 chapters in it on atmospheric stability. And this other book, which is called Instabilities and Skew-T Diagram and Photographs. This is a book that's put out by the Weather Graphics, which is a service. It's run by a former Air Force meteorologist, and their books tend to be for storm chasers, but the information is simplified so that we can all understand it.
Very good. So there's some homework assignment for you for our next session when Dr. Bartuska will join us again in December. And so one of those documents I have in my library, the Aviation Weather book, the other one I will soon get. I've also learned a good bit from another meteorologist, Dr. Scott Danstead, on his discussion of the skew-T diagram. And so there's a lot of good information that we're going to learn from you the next time we get to visit with you. Until then, we're just going to have to let our knowledge lapse until December, and we'll see how that works. So thank you very much for joining us today in the last segment of today's Plane Time with our guest, Dr. George Bartuska, and a very interesting discussion on weather. So I'm Ron Timmermans, one of the many hosts for the Florida Aviation Network. Thank you so much for joining us today, and we will see you again in December for another version of Plane Time.